Homework 8, problem number 5. It is desired to conduct experiments in a water tunnel in order to experimentally measure the drag on a car. If the prototype condition is a velocity of 50 miles per hour through air, and the model is 1/5 the scale of an actual car, how fast should the water flow in order to achieve a Reynolds number similarity, matching RE between prototype and model?
My Australian half-brother is always bragging how he can save people 15% or more on their car insurance. Well, take this, Mr. Gecko. I'm going to show the students in CE 340 how to solve problem 5 from homework 8 in under 5 minutes. First, I like to think my process as a recipe. We're asked to find the Reynolds number. The Reynolds number is equal to the velocity times the characteristic length over the kinematic viscosity. And looking at our problem, we can see that for the actual conditions, which is the car and air, the velocity that was given was 50 miles an hour. The kinematic viscosity of air is 1.57 times 10 to the negative 4 feet squared per second. And the length, which for a car is considered the width of the car, we'll just consider a generic L. For the model car, which is in water, we are looking for the velocity, which we don't know. We'll call this variable x. The kinematic viscosity of the model, which is in water, is 1.21 times 10 to the negative 5 feet squared per second. The length is 1/5 the length of the actual car. For step 2, we like to mention what we are actually looking to find. Again, we're asked to achieve Reynolds number similarity, so we need to set the Reynolds number of the actual conditions equal to the Reynolds number of the model, and in doing so we'll find the velocity of the water, which we labeled x. For the third step, we set the Reynolds number of the actual conditions equal to the Reynolds number of the model. As you can see, we've done that. We then substitute in our variables we defined earlier in step 1. As you can see, the lengths cancel out, and we get an expression for x, which is the velocity of the water, 5 times velocity of the air, times the kinematic viscosity of the model, or the kinematic viscosity of the air. Simplifying, we see that the feet squared per second cancel out, and we're left with x, which is the velocity of the model, equal to 19.2675 miles per hour.